Welcome to Math 119, Chapter 6.3, where we talk about logarithmic functions. So logarithmic functions take on the form f of x is equal to log a of x. Now, if you're curious as to how to actually say this, this is just log base, or just log a of x. And you'll notice this little a down here is smaller than the log or the x. It is actually acting as your base. So in this case, your base is a, very similar to what we talked about your base being from before in your exponential. Now in your exponential function, for example, we'll just take this as f of x is equal to e to the x. So it's your natural exponential. Can you pick out your special features of this graph? Maybe even your domain and range. So some of the special features that I'm hoping you found is that your x-intercept, do you have one? Now you don't have an x-intercept, but what perhaps is the reason behind that? Well, this is because you have a horizontal asymptote. Your horizontal asymptote at y is equal to 0, right? This was the dotted line we talked about before, where we just cannot cross when y is equal to 0, which would provide us with an x-intercept. But because you cannot cross this particular dotted line, we're not going to have an x-intercept. But does that mean we have the opposite? Do we have a y-intercept? We do have a y-intercept at 1, 0, meaning we don't have a vertical asymptote. So we don't have a vertical asymptote, but we do have a horizontal asymptote. Now, if we were to talk about your domain and range here, your domain would be all real numbers, but your range would be from 0 to infinity. And we talked about that from our last class. Now, logarithmic and exponentials are inverses of one another. So take a look at your logarithmic function and what do you notice? So what are your special features? So again, try and pause the video and see what you can come up with. Well, your x-intercept, we finally do have one at what looks like it is 1, 0. What about your y-intercept? Your y-intercept, we don't have one. And why do you think that is? Well, this time we do have an asymptote, a vertical asymptote, what looks to be like, instead of at y is equal to 0, we have one at x is equal to 0. So we have a vertical asymptote at x is equal to 0. And your horizontal asymptote, we do not have one. So notice that those two are flip-flopped as well. So an x-intercept, we didn't have one, but now we have one. Your y-intercept, we have one, but now we don't have one. Your horizontal asymptote, we didn't have one, or we had one, and now we don't. And your vertical asymptote, we had one, and now we didn't have one before, but now we do. In your domain here is going from 0 to infinity, non-inclusive because of your asymptote. In your range, this time is all reals. Notice that they are again flip-flop. So what's the name when everything has been kind of reversed? This means that these are inverses of one another. So exponential and logarithmic functions are inverses. So does the exponential function pass the horizontal line test? Yes, it does pass the horizontal line test. And if we were to reverse everything, we have your logarithmic function, and vice versa. We have a horizontal asymptote a horizontal line that passes, and we have your exponential. And we can see that here as well. If I were to have all of my points listed, so you can see that x is equal to y line, that's the black line, that is our reflecting line that we get to immediately reflect all of your x and y values over. And you'll notice that the green line is your Your green line is your exponential, your purple is your logarithm, and they are just going to be flip-flopping those domains and ranges and all of those special features that we talked about where we talked about your asymptotes and things. We have all of that information down below, as you can see here. I've just put it into your graph. Now, because these are inverses with one another, what we can do is go from one form into another. So if we have an exponential and we want to map it to a logarithm, well, we're going to take your logarithm, right? Your exponential, so sorry. This is your exponential form, and we want to turn it into a logarithm. The first thing we want to do is identify your base. Your base here is just going to be called a for now. So we have a to the y is equal to x. So when we go and try and use it into a logarithm, well, the first thing we need to do is write the word log. Then we get to write your base next. And then from here, it's called the swoop method for now. What we do is you start on your base, you're going to come up and around x and land on y, your exponent. And the way that you're going to swoop is the way that you write. The first thing we write is your base. The second thing we come close to, and even if you wanted to redraw it where you touch, so notice I'm touching on A. This is the very first one I touch on. We touch x and then we touch y. So the way that we touch is the way that we write it. So A first. The next thing we touch is x. So this is the next thing that I write. X is equal to the last thing that we touch is your y value. So it's equal to y. And notice that it goes, I wrote y and I put a 3. Notice that it goes from an exponential, so something raised to a variable, and then written as a logarithm. Now we're going to take this property and apply it to these ones. So we'll take all of these exponentials right here, A, B, and C, and we are going to use your swoop method and write it in a logarithm. Now, if you don't like the way in which you swoop, right, you can always write equals 8 if you prefer that way, right? But the first thing to do is write log. Notice that we go from an exponential to a log. So to go to a log, you need the word log. So we're going to start on 2, come up and around 8, and land on your 3. So the next thing we write is 2 down below. 8 is equal to 3. And again, notice that your bases need to match. You have a base here of 2, which has to match the logarithm base. Let's have you try it again here. So first thing to write is log. Then if you like the swoop method, we're going to start on 5, come up and around, and then land on 4. So we have log base of 5, 625 is equal to 4. One more time. You must write log first. 7 up and around x and land on z. 7 x is equal to z. And again, you always want to make sure that your bases are all equivalent. Now we're going to take the time to go backwards as well. So we're going to start on a logarithm and go to an exponential. So you'll notice that here we have your log of base a. So again, we'll try that swoop method again. And to go from a log to an exponential, because it's not a logarithm, we don't have to write the word log first. Instead, we start on your base, we come up and around y, and we land on our x. So the first thing we want to write is a. Then the second thing we write is y is equal to, and the last thing we write is the last one you land on, your x. So it goes back, snaps right into your exponential, where again, your base is the very base that we have from above. So let's try that again over here. So we go from 5 up and around x and land on 25. 5 to the x is equal to 25. And if I said, hey, could you solve this one for me? What would you say x is equal to? Well, x is equal to 2, right? 5 squared is equal to 25. Now, if we wanted to solve something like this and it's in a logarithm and we were trying to figure out, well, I don't know how to type it into a logarithm quite yet into the calculator, but perhaps I could evaluate it as an exponential, right? We could say is equal to a question mark or is equal to an x, and then we again can try to swoop and find your equation. So come up and around and land. So you can say 1/2 to the x is equal to 2. Meaning, what does x have to be in order to equal to 2? Well, keep in mind, if this is x here and a 2, we're looking at elementary cases and how to solve them. So if we have 1/2 and we have a 2 on the other side, well, could I make it so that this one isn't 1/2 anymore, but it instead has a -1 to the x is equal to 2? Well, they both have the same base. So we now take a look at your exponent. Your exponent on your 2 is 1. So we have -1 times x is equal to 1. So x has to be equal to -1. And if we were to check that that is true, right? 1/2 to the -1 is equal to 2. We'll keep change flips as we now have 2 to the first power, which is equal to itself. So that would be correct. Let's try it again. Is equal to x. Come up and around. So we have 17 to the x is equal to 1. So what would be x equal to? Well, anything to the what power is equal to 1. Well, x has to be equal to 0 for that to be true. So 17 to the 0 is equal to the first, which is actually true. So again, this is why it's going to be useful to go from a logarithm into an exponential if we're trying to solve elementary cases. And again, if there's no variable, but we are trying to solve and figure it out, because again, on your test, you're not allowed a calculator. So this is perhaps a way that you could solve it without punching it in. Now, let's have you pause the video and try it one more time using your swoop method on the following. So we have a to the, I'll say x. So we want to figure that out. If we were to swoop, we would write a to the x is equal to 1. Therefore, x has to be equal to 0. So it just means a to the logarithm, log base a of 1 is equal to 0. So if, right, these are properties of logs. Now, these are more generalizations. If you have any sort of log base, but it's coming out to be equal to 1, so 1 on here, that just means that it's going to be equal to 0. Because again, you can always swoop to double check that your base raised to what power is equal to 1. Well, that has to be 0. So again, over here, if we were to swoop, we had a, and I'll just write x, a to the x is equal to a. Then what is x equal? Well, let's say a, because your variable exponent isn't showing, it's just saying that x is equal to 1 over here. So that just means that this x over here has to be equal to 1. So as you're looking at it, if your log base here matches your numerical number over here, then they will actually cancel and be equal to 1 itself. Now let's take a look at this one. So again, we can write just x if we want for now, but we say a to the x is equal to a to the x, because again, if you swoop, right, we should have a to the x and a to the x over to the other side. So x is equal to itself. So that just means this whole thing, actually, I don't even have to erase it. This whole thing is equal to x. The reason behind this one If we don't want to use swoop method, eventually what we can do is that we have a logarithm here with a base of a. Right? We have a logarithm with the base of a, and we have an exponential, right, a to the x, with, again, your base matching the a from before it. So if you have one inside of another, they're going to cancel each other out, and whatever is left over in your exponential, it will just drop, and that'll be equal to whatever we're looking for. This is your inverse property at work. Think about x squared under a square root, right? Well, they both cancel each other out, and it just comes out to x. So if we had 2 squared, or if we had 3 squared underneath a square root, right, they're going to cancel, and it'll just be equal to 3. You don't need to actually say, okay, well, this is 9, square root of 9 is really 3, and you're just going to be left over, right? It's just using that inverse property to your advantage and just getting your x equal. I'll leave that one up. I'll erase this part. And let's try it again. So we'll put that over here. And if we're trying to swoop, right? And again, we don't have a logarithms to start. So it says log base a of x is equal to your exponent, which is just itself. So it's going to be equal to, again, itself, x. But using your inverse property again, if we wanted to, we have your exponent base being raised to a logarithm of the equal base. So your bases once more cancel, and this x drops. It is itself. So x is equal to itself. So if I were to generalize this once more, so if I said this one could be rewritten as the square root of x squared, this one could be written as the square root of x all squared, right? Because you can have two things. You could say, okay, well, I'm going to square this one first and then square root it. The other one says, I'm going to square root it first and then square it, right? It's just the order in which you would have performed your value, your operation. So again, these will cancel and it'll drop. So if we wanted to write the following from the above, we wouldn't have to use your swoop method. So if I were to erase really quickly over here, this first one, right? As long as I knew that my base here was 2, I could rewrite it. So it just says log base 2. What I do to one side, I do on the other side, log base 2. I allow this to cancel and 3 drops. So we have a log of 2, or sorry, log base 2 of 8 is equal to 3, which is exactly what we got from before. If I were to go in the reverse, so I'll erase really quickly this one. If I were to go into the reverse, right, well, I have a base of 5 here, so I get to write everything to the base of 5 as an exponent. What I do to one side, I do on the other. So what it allows me to do is that it cancels with my logarithm and my 25 comes down. So I'm at 25 is equal to 5 to the x, which means x, again, has to be equal to 2. I'm a huge fan of writing it in this method, rather my swoop method, because it actually forces you to write the word logarithm on all of these, or being raised to the 5th power. But it's up to you in terms of which method you're going to like. Now, before we move on to example 3, I'm going to have you try a couple quick questions. Let's have you try 7y is equal to 4, log base 3x is equal to 2, now is equal to 9, and one more. 7 for x is equal to 1. No, let's do 2. Okay, so see if we can rewrite these as its opposite counterpart using, instead of the swoop method, let's try to use the inverse method. So if we have a base of 7, what we're going to write is taking the logarithm of that equivalent base 7, so log base 7. That way that these will cancel, your y drops, and we have y is equal to log base 7 of 4. We could, if we wanted to, punch that into our calculators later, which I believe that'll be in a separate video. Yeah, so that'll be in a separate video for how to punch these into a calculator. So let's try that again. For this one, we have a logarithm already with a base of 3. So that just means we write your base of equivalent base 3 as the exponential, and this becomes now its power. What you do to one side, you do to the other. It allows us to cancel, and this one drops. So x is equal to 3 to the 9th. And then again, you could punch that into a calculator. One more. So again, we have log base 7, log base 7. That allows us to cancel. Drops. 4x is equal to log base 7 of 2. And if we wanted to solve for x here, we could then go ahead and divide everything by 4. Now, log base 7 of 2 is going to be a number. So we can't just say, okay, well, this is now 1/2. That's not how it works, because this value is a number. So it must be divided by the whole thing by 4. So now that hopefully you feel a little bit more comfortable taking the equivalent place, let's take a look at example 3. Now, example 3, I wrote b incorrectly. So this should be not x in the over there, but it should be x over here, or if you prefer 2x right there is perfectly fine. So if we look at example A, we have log base 2 of 2x is equal to 1. Now, this 2x is not the base of your exponential. Instead, these are just numerical. It is just a variable and its coefficient. So instead, right, we want to get this log of 2 to cancel, meaning that we want to take 2 to either side. That will allow us, now that our bases match, to then go ahead and cancel and allow this 2x to drop. Is now equal to 2 to the negative first. So solving for x here, we want to get x alone. We might want to consider rewriting this 2 to the negative first power as 1/2. And again, dividing by 2 here, or multiplying by 1/2. It doesn't matter the way that you look at it. What you do to one side, you do to the other. So we have x is now equal to 1/4. Again, the reason why these 2's don't automatically cancel is that this is not an exponential. This isn't 2 raised to the x power, in other words. Now try B. Now notice that we already have your exponential base of 3 matching the exponential, or sorry, the base of your logarithm. So these get to cancel, and our 2x drops, which is then equal to 2. So x, therefore, is equal to 1. So that is using your exponent, your inverse property. I have one more for you to pause the video and try on. So you have log base 2 of 8 to the x is equal to 5. So believe it or not, we don't have to actually write it like, you could do one of two things. First being, we can raise everything to the second power. That way it matches here and will cancel and allow us to drop and have 8x to the 2 to the 5th. So 8x Oh, but if you were asked to solve for x, right, rather than saying, okay, well, 8x is equal to 32, right, and then trying to figure it out that way. Well, what do you know from our previous lecture about 8 to the x is equal to base 2 and then to the fifth? Well, we want to get your bases to match. So instead, let's rewrite 8. 8 can be written as 2 to the third power of x is equal to 2 to the fifth. So we have 3x is equal to 5. Therefore, x is equal to 5 over 3. And again, we can always certainly check your answer. Now, let's say we didn't want to do that, but instead we understood that before we started, right, 8x could be rewritten as 2 to the third x, if you prefer, or 2 to the 3x, right, multiplying out those exponents. Therefore, now that your bases match, it'll cancel, allow us to drop and say 3x is equal to 5. Therefore, x is equal to 5 over 3. Now, notice that those equations that x is equal to the same exact thing. It's whether or not you understand the numbers patterned first, or once you take a look at it and you're still asked to solve it, that you can go from there. I really like this question. I also actually really like some of the ones before it, like E, I really enjoy. F, I also really like as well. Now, there are some logarithms that pop up a little bit more frequently than others. So logs that have a base of 10 are called common logs. This is what your calculator normally does when you type the logarithm button on there. It just is a logarithm. So if there's no base, you're going to assume that it is a base 10. So logarithms, instead of writing log base 10 of x, what you can do is you just get to erase that little 10 or just rewrite it to just say log of x. So if you don't see the base, you're going to have to assume that the base is 10. So its inverse counterpart is 10 raised to the x. Now, logs that have a base of e are called natural logs. So you either have a common log or a natural log. Natural logs, right, typically they're not really written as log base e of x. Instead, they're written as ln natural log e of x, or even better, just ln of x. And again, assume that there's an e there, just like you did with your 10 here. So the inverse of it is just e to the x. So if you can, pause the video, whether you want to do the swoop method or the inverse method, see what you can come up with the following properties. So ln of 1, right? Again, your hidden figure e here. Let's just do x. We can swoop and say e to the x is equal to 1. Therefore, x has to be equal to 0 in order for that to be true. So we can erase here and put 0. Over here, we have e to the, or ln of e with a base of e, right? That'll cancel, right? And whatever the exponent was on top, which in our case is just a 1, will drop. And so our value is equal to 1. Or you can swoop and say e to the x is equal to e, or e to the first. Therefore, x is equal to 1. Over here, once more, we have the hidden e, which we have those same variable or the same base, which allows us to cancel. And so the x drops. So we have just e to the x. So e to the x is equal to e to the x. So it's just equal to itself. And I think we have one more, which is the opposite counterpart. So we have an exponential base of e with the ln base of e, so they'll cancel once more. X drops, so it's itself. So those properties are the exact same as the one before it over here, just with your natural log. So see if you can pause the video and try out example 4 for yourselves. So we have ln of the cubed root of e. So we're going to rewrite this one as ln e to the 1/3. And I want to know, well, what does this come out to be? Well, we have ln of e here, so these will allow us to cancel it out, and this drops, so our answer is just 1/3. So we have log of 1,000. So let's rewrite this here. So I have a logarithm with a base of 10, right? If you don't see it, it's a base of 10. And 1,000, right, is really just 10 raised to the 3rd power, which allows us to cancel, and the 3 drops. So let's try it over here with 5. So again, this is really just log base 10 of 5 is equal to what? Well, it just says 10 of, I'll just say 10 of x is equal to 5. Well, in this case, we would actually need to figure it out with your calculator because we cannot evaluate either of these as we normally would. However, we could just use that same setup. So it would have to be one or the other. Actually, this might be a good time to show it how to punch it into your calculator. So we'll go over to a TI-84. So if you wanted to evaluate a logarithm with a base of 10, your log is on the left-hand side, located right next to the 7. Notice that when you hit it, it does not come up with the little base that has 10, and it doesn't allow you to put in a numerical value. So we could instead just say what our value is, 5, and then it'll estimate it for us. Over here, we have ln of e, which is equal to e, of e to the negative 1st power. So again, these will cancel and allow that -1 to drop. So it's equal to -1. Now, once more here, we have log of 0.001, which if we were to rewrite it, we have log base 10. And this could be written in scientific notation. If we just move your decimal point over, we have 10. And because it's an incredibly small number, it's really to the -3rd power. To get into that scientific notation, we can push it over to, in our case, because it's small and going to the right, it's going to be the negative. And however many decimal places that you want to move it to is the one over here. So again, these will allow us to cancel, and the negative drops. You could also think about it as a fraction as well. This could be written as 1/1000, or 1,000 to the -1, which is then 10 to the 3rd times -1, or 10 to the -3. Lots of different ways to kind of wrap your head around that particular one. Well, hopefully this video was informative and allowed you to understand the properties of logs and really how to use whether the inverse function itself, the inverse properties, or just the swoop method.